Okay, everybody, welcome back. It's been some time. We're going to jump into Chapter 6. We'll take a look at Section 6.1 now, which basically is just a bunch of terms and definitions for probability, just kind of getting our feet wet here, okay? We'll talk about things like chance experiments and events and some other vocab. All right, so I recommend have your notebooks ready, write out whatever notes that I'm posting, pause as you need to, take your time, and do your best. If you have any questions, shoot me an email, all right? Okay, so first thing we talk about are some vocab words here. We have what's called a chance experiment. And in the land of probability, that's just any activity in which there is uncertainty about which of two or more outcomes will result. Examples could be as simple as, say, flipping a coin, right? Every time you flip a coin, you're going to get a head or a tail. You don't really know. That's a chance experiment. Roll a standard six-sided die. You're going to get 1, 2, 3, 4, 5, or 6 every time you roll. Okay, that's an example of a chance experiment. There's more than one possible outcome, and you really don't know which outcome will result until you do the thing. All right, so talk a lot about chance experiments in this unit, and that just means whatever activity that has more than one possible outcome. Okay, next up is sample space. That's the collection or set of all possible outcomes of a chance experiment. We write these as either ordered pairs or triplets or etc., basically in parentheses. Or we can represent sample spaces as a tree diagram. So let's take a look here. Okay. Consider the chance experiment of flipping a fair coin twice. Okay, so a fair coin, heads and tails, 50-50 shot of landing on either side. Represent the sample space as ordered pairs and in a tree diagram. So let's think about all the possible outcomes we could get if we flipped a coin twice. So we make a little squiggly bracket, and in a parenthesis, we're going to write the possible outcomes. So for example, we could get a head on the first and a head on the second. That's one potential outcome that we could get when flipping two coins. What else could we get? We'd get a head on the first, a tail on the second, a tail on the first, a head on the second, or we could get two tails. All right, and that's all the possible outcomes that we could get. So what we've just done is listed a set of ordered pairs that represent the four outcomes when flipping a coin twice. In terms of a tree diagram, these can sometimes be a little more helpful in terms of being able to compute probabilities a little bit later in the section. So for a tree diagram for this, we start in one location, and we're going to have a branch for each possible outcome. So I could get a head on the first flip. I could get a tail on the first flip. That's what that represents. Regardless of what I get on the first flip, when I flip a coin a second time, I still have two possible outcomes. Get a head or a tail. If I got a tail on the first flip and I flip again, I could get a head or a tail. Here's a tree diagram representing the possible outcomes. Each of these paths represents one of four possible outcomes here. That would be getting a head and a head. This would be head first, tail second. Tail first, head second. Tail first, tail second. Okay? And with the tree diagram, we can actually write in the probabilities along the branches. What's the probability I get a head when I flip a coin? Well, that would be 1/2 or 1 out of 2. Probability I get a tail is 1 out of 2. Regardless of what I get on the first flip of the coin, the probability I get a head on the second flip or a tail on the second flip is 1/2. Same thing if I had gotten a tail first. So tree diagrams can be a little bit more detailed than our ordered pairs, but again, basically represents the total number of possible outcomes. If you count the total number of bottom branches, as I call them, that gives you the total number of outcomes. There was 1, 2, 3, 4 different possible outcomes when we flip a coin twice. Okay. Now consider the experiment of flipping a coin and rolling a die. When we talk about a die in here, we're going to assume a fair six-sided die. List the sample space as ordered pairs and in a tree diagram. So I'll actually do the tree diagram first here. So we're going to flip a coin. Now, two possible outcomes when we flip a coin. Head, tail. Now, regardless of what I got when I flipped the coin, and again, I had a 1/2 probability of getting either. If I get a head, now I'm going to roll the die. Well, there's 6 possible outcomes on the die. So I'm going to have 6 branches coming out of this. and I could get the numbers 1 through 6, each with a probability of 1/6. I'm not going to label each individual branch just because it would get a little tight in there. Okay, but that's the idea, and then repeat for if you got a tail first. Okay, and again, each of these has a probability of 1 out of 6 along those branches. If I count the total number of bottom branches, that's 12 total possible outcomes. A head with the numbers 1 through 6, a tail with the numbers 1 through 6. Okay, so again, 12 possible outcomes here. And now if I follow the paths, I can get my ordered pairs pretty easily. So maybe it's easier to do that before listing as ordered pairs, but either way. Okay, so I could get a head with a 1, with a 2, so on and so forth, all the way up to 6. And then I could get all the same with the tails. Oh, and I already have it written right there in blue, okay? And that's fine with or without the parentheses. Okay, so look, I'm just going to clean it up and finish writing it like I have with the parentheses. That's more likely the way you're going to see it than not. Okay, so once again, we have a tree diagram to represent the situation. We also have the set of ordered pairs, listing all potential possible outcomes, okay? Prime number, we're going to see this number, this term come up a little bit. So just remember, a prime number is a positive number that's only divisible by itself and the number 1. Okay, 1 is not a prime number, okay? The prime numbers, well, the smallest prime number and only even prime number is 2. Then 3, 5, 7, 11, and so on and so forth, okay? But there's a handful of examples of prime numbers, okay? Another vocab word here real quick. Okay, we have an event. An event is any collection of outcomes from the sample space, okay? So any possible collection of outcomes. If we go back here and we look at these 12 potential outcomes, what's the event that we get a 3? Well, that would be either getting a head with a 3 or a tail with a 3. So that's one potential set of outcomes from our entire sample space. Okay, so the event is any collection of outcomes from the sample space. For example, what would the event resulting in heads and a prime number look like for our previous example? Okay, so we're talking heads and a prime number. So that would look like getting a head with a 2, a head with a 3, or a head with a 5. Those are the possible ways to get a head and a prime number. So there would be 3 possible outcomes for that event. Okay, some more vocab coming up now. Let A and B denote 2 events. Okay. Not A is the event that consists of all outcomes that are not in event A. This is known as the complement of A. Okay, so for example, suppose I roll a die and I say let event A be the even numbers. Okay, so that would be 2, 4, and 6. The complement of set A would be all the other outcomes that could happen that aren't in set A. So in this case, that would just be the odd numbers, 1, 3, and 5. Okay, so not A is just the opposite of what's in set A, whatever's left over, so to speak. Okay, now the notations for this come in 3 ways. The one I use the most is called A bar. Okay, a line over the A is how we write not A. Don't confuse that with the average value of A, like we do X bar earlier in the course. Okay, this means for probability, the opposite of A or not A. Another way to write it is with a little superscript of C. That's a way to say the complement of A. And yet another way is with a little prime symbol. Okay, so any of you who have taken calculus, this has nothing to do with derivatives. In this case, this all represents not A. Okay, an example. If I say A is the event that are even numbers on roll of a die, so event A would be 2, 4, 6. Well, in this case, not A would be all the other possible values we could get that aren't in set A, which would be 1, 3, and 5 in this case. So that's what's meant by the complement. Okay, or A or B, event A or B. This is the event that consists of all outcomes that are in event A, event B, or both events. Okay, not one or the other, but one, the other, or both. This is called the union of the two sets. Okay, the notation for this is like, it looks like a capital U, A union B. And we'll do an example in a moment so you can see, how this works. Next up are intersections. This is A and B. These are values that A and B have in common. Okay, they consist of all outcomes that are in both events A and B. This is called the intersection. The notation here is basically an upside down U. It almost looks like the letter A without the little line across the middle of it. Okay, A and B. And there's the notation for that. Okay. Now, another vocab word, independent events. Those are two events whose outcomes are not affected by the outcome of the other. Right? One event occurring does not influence or is not affected by the other event occurring. The probability of the second event occurring is not affected by the first occurring or not. For example, suppose we flip two coins. What we get on the first coin flip is not going to influence what we get on the second coin flip. We could get a head on the first flip of the coin. That's not going to make a difference if whether or not we get a head or tail on the second flip. They have nothing to do with each other. Okay, those events are independent. Roll a die and flip a coin. There's another example. When I roll the die, I can get 1 through 6. Well, whatever I get on that, that's not in any way going to affect what I get when I flip the coin. All right, so they don't have an effect on each other. They're called independent events. Okay. On the other hand, we have dependent events as well. Those are two events where the outcome of one does affect the outcome of the other. The first event occurring or not is going to change whether or not the second event, the likelihood the second event occurs. So for example, suppose we have an urn, right, like a bowl containing 3 red and 3 blue marbles. We're going to draw one marble. We're not going to put it back in. We're going to take it out, look at it, and then we're going to draw a second marble, right? So think about what's going on here. If I drew a red marble first, all right, the probability I get red, well, actually, let's take a look at the tree diagram for this situation. Okay, we have 3 red and 3 blue marbles to begin. So we'll have red, we'll have blue. Well, the probability I draw red is 3 out of 6. The probability I draw blue first is 3 out of 6. I'm going to give these little subscripts of 1. Now, regardless of what color I drew first, I could get a red second or a blue second. Red second, blue second. But now look, if we drew a red marble first, now and we don't put it back. That's the thing here. We look at it, we take it out, we don't put it back. Now there's only 2 red marbles out of a total of 5. And there's still 3 blues out of 5 that remain. Remember, we took one out. Now let's assume that we drew a blue one first. If we drew a blue marble first, there's still 3 reds out of a total of 5 that are left. But now there's only 2 blues out of a total of 5 that are left. So what you're looking at is, say, like the probability of getting a red marble second. Depending on the outcome of the first result, whether we got red or blue first, is going to affect the probability of getting red second or even blue second here, okay? That's dependent events, when the probability of something is affected by what happened before it, okay? And, we got to get these terms down because as we progress through this unit, what we'll see is that, like, computing probabilities often is dependent on the type of events we're dealing with, okay? So those are dependent events. Whatever happened first does have an effect on what happened second, can change the probabilities. And then we have mutually exclusive events. Those are two events whose outcomes cannot possibly occur at the same time. If A and B are two mutually exclusive events, then, and this is how we write probability, capital P, and then in the parentheses is what we're talking about. If A and B are two mutually exclusive events, then the probability of events A and B occurring together, the probability of that intersection is 0. Can't possibly happen. For example, suppose we flip one coin once. We can get a head, we could get a tail. We're not going to get both on a single flip of the coin. If event A is getting a head and event B is getting a tail, then the probability we get a head and a tail is going to be 0. No chance. Will not happen. Another example, let event A be it snows today. Event B is it did not or doesn't snow today. Good morning. Okay? It can't do both. Either it did snow today at some point or it didn't, so the probability of events A and B would be 0. Okay? And last up, we're going to talk a little bit about Venn diagrams here, and we'll continue this conversation in the next lesson. Okay, a Venn diagram is a visual way to represent sample spaces. If two events A and B intersect, we would draw two circles that overlap, as you see in the example here. If A and B were mutually exclusive, we would draw two circles that don't overlap, like this. Okay, but let's assume we have two events that can overlap. The rectangle represents what's known as the universe. It's just your whole sample set, okay? Excuse me. And then each of the regions has meaning here. Okay, this region right here would be the intersection. Those would be all elements that are common to both sets A and B. That region is the intersection of sets A and B. Okay, that's basically the region A and B. Okay. Over here, this is stuff that's in set A only, but not in set B. Now, notationally, I could write this as section A and not in section B. Over here, similar stuff that's in set B, but not in set A. So in B and not in set A. And then this region outside of all the circles is the stuff that's not in A and not in B. Okay, that's all the leftover stuff. So let's take a look and get a sense of how we label a Venn diagram. Okay, create and label a Venn diagram for rolling a die. The possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. There's our sample space. Let event A be the event that we get an even number. Let event B be the prime numbers. Okay. So what we got to do is we're going to put the numbers for the possible outcomes of the die roll. They're all going to go somewhere in this Venn diagram. Okay. Now, even numbers are 2, 4, and 6. Prime numbers are 2, 3, and 5. Okay. So look, are there any numbers that are common to both sets? Well, yes. The number 2 is both even and prime. That goes in the intersection here. Okay, and I'll cross that off. We've accounted for it. Now, let's look at the even numbers that are not prime. Well, that's 4 and 6. So they will go in circle A. Let's look at the prime numbers that remain, 3 and 5. They will go in this section. Are there any numbers left that aren't even, aren't prime, that we haven't accounted for? Oh yeah, the number 1. So that will go outside. It's not even, it doesn't go in the A circle. It's not prime, it doesn't go in the B circle. It's neither. Okay? And now, we could ask a couple questions. What value is in the intersection? That's what's ever in the A and B region. That's common to both. That's just the number 2. What values are in the union? That's A or B. That's what's ever in circle A, circle B, or both. So that's all that stuff. 2, 3, 4, 5, and 6. Okay, so there's a quick introduction, mostly emphasizing terms, definitions, tree diagrams, and a little bit with the Venn diagrams. More to come. Hang in there.